And now we will have the last paper in the session number 3. So the paper will be presented by Paulo Tavares, coming from Portugal, from Porto, Inegi from Porto, and the paper is entitled Robust Reference System for Digital Image Correlation Camera Recalibration in the State of Fieldwork.
So, good morning everyone. I will do a very short presentation on the issue of digital image correlation. But we decided to bring this presentation because we're very excited. It's a very recent result, and we're very excited about this result. The work has been done by one of our students, that's Francisco Barros, in the Optics and Experimental Mechanics Laboratory. That's our unit in Inegi. And this is a unit mostly devoted to monitoring in experimental mechanics. We have been doing monitoring with coherent laser sources for many years, and in the recent past, like 8 years ago, we started working on other methodologies such as digital image correlation, thermographic methods such as thermoelastic stress analysis, and so on. So at some point we have been asked to do measurements in fieldwork with digital image correlation. So we're accustomed to do measurements on very small samples in mechanical engineering, mostly in tensile testing, and in fieldwork it's huge 3x5 walls in concrete or bridges or whatever. So that's the sort of range in measurements that you have to deal with with digital image correlation. And when it comes to fieldwork, you know that a number of issues arise that question the robustness of the method, and you have to start developing your own algorithms because commercial systems don't respond anymore to some of those issues. If you talk about illumination issues, for instance, when you're doing field work, they pose a lot of problems to your measurements, and the results are not accurate enough with commercial systems. So you have to develop your own algorithms to be robust to intensity changes in lighting, for instance. And another issue that arises very frequently is the fact that if you're doing a measurement in field work and you want to return to that measurement after some time, you just cannot, well, you can try to leave the cameras there and not move them at all, but that's not feasible in many circumstances. So you have to take out the equipment and return to the measurement sometime afterwards. But then you have the problem of calibration, because you lose your calibration and you cannot relate your measurements with the previous measurements any longer. And that's the problem we've been dealing with, and we're so excited about. So anyone who's been working with digital image correlation in 3D knows that calibration can be a challenge. If you so touch the tripod with your two cameras, or the cleaning lady comes in Thursday morning and cleans the lab and touches the setup, your calibration is lost, and you have to start over every time such a phenomenon occurs. So if you want to do long-term measurements, you really have to deal with that sort of problem. And then your camera calibration is not valid anymore, and you have to perform full camera calibration, which is well, depending on the measurement specimen. If it's a very small measurement specimen, you need to use long focal distance lenses with very short focal depth, and then your calibration is very difficult to achieve. If you have to do it every time, it's a messy problem. And if you have to relate those measurements with the measurements that you were doing previously, that's even a further problem, because you don't know how to do that. So what we decided to do is to develop an algorithm that uses features in the scenery. And if you can detect those features from one instant to the next measurement, then you'll be able to translate and rotate your cameras to the positions they were in the initial measurement, and therefore, without recalibrating totally, doing a very small, doing a recalibration with the world positions of those points only, that you'll be able to continue the measurements from the previous instant. So the problem of detecting points from one measurement to the other, from one image to the other, requires a very robust feature detection and tracking system. We've been using an algorithm called SURF that's speeded up robust feature detector. If you know anything, well, if you're accustomed to dealing with feature detecting and tracking, you know that's basically a two-step problem. You have to detect features on your images, such as corners or small points, and then track them to the remaining images. But in order to do so, you also need a descriptor that's mainly a vector that will describe the neighborhood around those features, and that will enable you to go from one image to track that feature exactly from one image to the other. And that's the sort of thing we've been doing. So in order to test the algorithm, we've developed the algorithm to do that. And in order to test it, we performed a simple setup, tensor setup. And you can see, okay, yeah. So you have a specimen. It will be elongated 5 millimeters, but we've placed some patterns around, just behind the specimen and around the specimen, so we could be able to detect features on those images. You cannot clearly see the fact that the speckle pattern on the object, because it's very dark. It's a dark rubber or a dark elastomer. It's a foam, actually. And you can see it better here. It was painted with white dots instead. So it was like elastometer, and we've painted with white dots. So we've placed those objects around, so we could detect features there. And then what we did was, so we took an initial image, a reference image, then we elongated the specimen 5 millimeter. We took a second image with the same setup as it was. Then we took the setup away, brought it back to another position. You cannot exactly put it in the same place. Refocused the cameras, and then with the detected features, we were able to track those features from one setup to the next setup, and from those features we could calculate the new camera positions, and therefore we could do a recalibration of the setup automatically and position the images as if they were looking through the initial camera positions. So basically, we can continue the measurements. So there we have it, initial setup. This is a pair of images, left and right camera. And then you load it, so you can see from the comparison here and there that we're loading some 5mm intention. And then we go away, bring the setup back, refocus the thing, and it automatically recalibrates and allows to continue the measurements. So then we perform a digital image correlation on the first loaded images, on the second recalibrated images, and obviously the point clouds from both images must be the same afterwards, or at least have an acceptable error, which was the case. So there it is. We're using this speeded up robust features detector, and we're using it to detect features. So actually, we're using this with a lot of features to detect. So this is an over-determined system, and we want as many features as possible. But obviously, while you're doing fieldwork, you want to find features on the field scenery, and you don't want to place them there as artificial features. You want to detect it as in some sort of stone features, or in the image some other features that you can detect and use for comparison. And from the triangulation of the points and the camera calibration, you can detect and calculate the 3D world coordinates of the points on the new calibration. So after it's been done, you can actually calibrate calculate the new camera position. So here you have it. So the blue dots and arrows are the original camera positions and orientations. You can see there, and the red ones are the new setup after it's been brought back and refocused. That was trying to represent the specimen over there. That's that tiny little thing. You can barely see in the image there, but it was a specimen seen. This is the scenery seen from above, obviously. And with that information about camera shift, you can actually continue your image calculation. So you can see here in black, the black dots here represent the reference state, and the green dots, you can see them a little bit above the black dots there, represent the measurement done after recalibration. These red dots represent what would have been the result if when we brought back the setup if the recalibration hadn't been done. And this is the digital image correlation that we're getting with the original calibration, and then with the new calibration. You can see that the errors that we get from the point clouds are very, very small errors, like around 50 micron. This specimen is a 200mm specimen. It was displaced 5mm, and the errors are around 50 micron. So there's obviously always an error in doing this, but it's quite an acceptable error. So we're looking at the mean error of around 37 micron, and the maximum of 65 micron in such a measurement. So you can understand it's a rather large specimen there. So what we've been able to do with this algorithm is to enable digital image correlations in correlation studies in fieldwork to be done regardless of the time spent. We can take the equipment home, bring it back, refocus the cameras, and we will continue. We'll be able to continue the measurements that we were doing previously without incurring in calibration issues, because we'll basically continue with the same calibration. So the idea of doing this work will be next to well, it is quite a challenge to find robust features that occur naturally in the field, but it can be done. Actually, we don't need as many features as were presented there. We're doing just to make the measurements more robust, but you can work with a lot less features. Also, if you work with less features, it will make the algorithm work much faster. I can tell you that right now, with that amount of features that we were looking at, those green points, the algorithm takes about 1 minute to do a new recalibration. So detecting the features and doing a recalibration takes about 1 minute to complete with that many features. So if you reduce the amount of features, you can work much faster in that respect. So it's a challenge, but it's an interesting challenge to find features such as corners or tree leaves or branches or whatever that you can find in the image and use them if you can track them from one image to the next one. So in practical fieldwork problems, if you're trying to do this kind of digital image correlation measurements in a bridge, for instance, you will be able to find, most of the times, you'll be able to find naturally occurring features in the concrete, for instance. Anyway, there's always this issue of degradation of those control points, which might require some extra work, but that's what we're now working on. So, thank you everyone for attending.
Thank you very much, Paulo.